Alright, in this video 2 of our calculus series, we are going to talk about slope. Now, slope is back algebra 1 actually, and slope was usually notated by m, and this m was generally equivalent to, let's see here, y sub, well, pardon me, this was generally denoted by y minus y naught, or the point, over x minus, drop my pen, alright, x minus x naught. Now, what did this mean? What did this mean? So if we have this graph, alright, and say we have this line, alright, we have this line, alright, the slope, alright, say we want to get the slope if we have this point here and this point here. What do we do? So what we would do is we would notate. We'd have this, okay? And this would be y minus y naught, alright, with this being the y value of this function, or of this point, and then this being the y value of this point. So we would subtract these, or we would also notate this sometimes as delta y. Might be a little more familiar. Down here you're going to have x minus x naught, alright, and that's going to be the x value here minus the x value here, or, as you would probably be familiar with, delta x. Now, that brings us back to the original formula. Here we are going to have delta y so we would have delta y over delta x. I'm going to make this font a lot bigger. Alright, this is a big point here. Alright, delta y over delta x. So, this is our slope. This takes us back a while. Now, when we talk about calculus, alright, we're going to talk about slope of a curve. Now, first let's talk about a secant line. A secant line. What is a secant line? Well, a secant line is going to be the average slope or rate of change between 2 points. So, say we have this funky looking curve, alright, and we want to get, actually this is not a very good example. Alright, say we have this funky looking curve, alright, and we want to get the slope, alright. What we're going to do is we're going to estimate the slope. So say we want to get the slope from here to here. Alright, we're going to get an average slope. Alright, so our slope is going to be this line here. Alright, this line is going to be estimated by delta y over delta x. This is going to be our slope. Alright, so we're going to have this line that's an estimate. Alright, now one thing you notice about this can be pretty inaccurate, especially if we're taking this over a long period of time. The farther and farther these points get apart, the more inaccurate they become. So say I want to do the average slope from here to here. Alright, so this line here is not going to be very accurate. Alright, now what this shows us is that the closer these points get to each other, the more accurate we're going to have slope at one point. Now, slope has been coined as velocity. Now, velocity is what we've been getting with secant lines. Well, generally we've been taking slope of line, so it's constant. But when you have a curve and you want to find average velocity, that's going to be average velocity. But what we're looking for is we're looking for instantaneous velocity. In other words, we're looking for the line, the slope of the line, that will touch this curve at one point, all right, and this will match the slope at that point. So this is what we want. Now, this line here is denoted the tangent line. Tangent line. So this tangent line here is what we're trying to find. All right, so this way we know the velocity exactly at a point. Now, how can we move those points closer and closer together? Now, last lesson we talked about limits. Now, what we want to do is we're going to take a limit. So, the closer and closer these points get, this y and y naught, and this x and x naught, they're going to become pretty much 1 point. All right? Now, what we're going to have here is, we're going to put this equation. So we're going to have the limit is at, or actually, we're going to have the limit as x goes to, x naught of, now, what we're going to do here is we're going to, instead of using y, we're going to use f of. So we're going to have small f of x minus small f of x naught Alright, no. F of x naught, right, over x minus x naught. Alright, now, another way this can be notated is as the limit as h approaches 0 of oh, okay. This is going to be the limit as h goes to 0, or as x goes to h, pardon me. That is, okay. Yeah, I knew something was fishy. Alright. No, it says h goes to 0. As h goes to 0 of, yeah. Small f of x plus h minus f of x over h. Now this is the more common formula you're probably going to see. So what this means, h here is going to be the difference between the 2 points you're using to estimate slope. All right, so here we have f of the second point minus f of the first point over the second point minus the first point. All right, here we're going to use h as a difference. Okay, so this is going to be the difference down at the bottom. This is going to be the difference between the two. And then we're going to add that difference here to get the second point. All right. Now, I think the easiest to calculate is probably with this. So, we're going to try to find the slope of the function. All right, we're going to have f of x equals, let's go with x. Add script here. Let's go with x squared minus 1. All right, and what we want to find is we would like to find the slope at x equals 3. All right. Now, how are we going to do this? Okay. First, we want to substitute this value f of x for f of, and we're gonna just evaluate. All right, so we're going to insert the equation, and we're going to go the limit as h goes to 0 of. Now, we have x squared minus 1. So f of x plus h is going to be x plus h squared minus 1. All right, that's going to be our f of x plus h minus. Now we are going to have we're going to have x squared minus 1 over h. Alright, so this is going to be what we want to evaluate here. So, right now we cannot evaluate because this h at the bottom, if we substitute h for 0, alright, we're going to be left with 0 on the bottom, which we do not want. This will be indefinite. Alright, now, simplify this a little bit. So, well, I don't know if simplify is the right word, but we're going to begin to evaluate this, let's say. So, the limit is h goes to 0 of. Alright, so now we're going to have, we will expand this. We're going to have x squared plus 2xh plus, then we are going to have a h squared. Now we're going to have minus 1 minus x squared and a plus 1. Definitely have to watch the negatives, they can trip you up. Alright, so we're going to have this big annoying looking thing. Alright, and now we're going to have all this over h. Alright, now some of this stuff can be simplified here. We notice this x squared and this x squared will divide out. And we also notice this negative 1 and this positive 1 will add out. And so we're going to be left with this 2xh plus h squared. Alright, so. Alright, so let's see here. Okay, so we're going to insert our equation once again. We're going to have limit as h goes to 0 of. That's going to be a little bit nicer looking. Alright, we're going to have 2xh plus h squared over h. Now, one thing you notice about this is there is a factor of h on top and bottom. So this annoying h that has been preventing us from simplifying this is now gone. It's not being annoying anymore. So we're going to have the limit as h, this h goes to 0 of. Now we can take out a factor of h on the top and on the bottom. So we're going to have h times 2x plus h over h times 1. Alright, now these h's will divide out, and we're left with something that we can easily evaluate. Alright, so we're going to be left with the limit as h goes to 0 of 2x plus h. Now this is pretty easy to evaluate here, and we're just going to be left with 2x. Alright, so this is going to be the formula for getting our slope, right? A lot of work, but here it is. Now, all we have to do here, since we want this at x equals 3, alright, we're going to insert equation, and we're going to say 2 times 3 equals 6, and that's going to be our slope at that point. Alright, so this is going to be how to evaluate your instantaneous slope. All the ones on the problems on the website will be pretty similar to this. So until next time.